I guess we don't need that on the recording. So the things that I was trying to get at yesterday, I was trying to model all the different mistakes that you can make when you're analyzing this two-body system. And there are a lot of them. Okay, we started out, I think, trying to put the weight of this thing as the tension on this thing. Okay, and saying that the weight of this thing would be the tension over here. The problem with that was, well, what was the problem with that? Run that by your neighbor really quick. Why was that not the thing to do? Why can't I just say that 2.5 newtons is this tension and 2 newtons is this tension? Because that's what almost everybody and their mother had on their whiteboard to start with. But why did that not work?
Accelerations are different.
Okay, Mara brings up one issue. If you do that, you get different accelerations because you'll get the same FU for both of them. Okay? And you'll end up with different accelerations. And that'd be weird because that would mean the string is like getting longer or something. Why else is it problematic to say that they have different tensions? Yeah, you?
The sum about fourth pairs. They're the same row, so it should be opposite. On both things should be the same force, a pair of forces.
You might. Yeah, it's an interaction. It's a tension interaction that's happening because of the string. We talked about strings previously. Strings just communicate force from one point in space to another. They don't change it at all. Okay? So in a sense, it's like this thing is pulling on this thing. Okay? Therefore, this thing is pulling on this thing. They're interacting with each other. The string is just communicating that interaction. So they have to be the same size, okay? So then we tried some other stuff. We tried saying that the tension was equal to the weight of one of them, the heavier one. But that's problematic because then you end up with balanced forces over here. I want like a little, can you guys see like a fly on the screen there?
Yeah.
I need like a little highlighter or something. I bet I have one. Boop. All right. So yeah, so if you tried to, oh, look at that. That's great. Now I feel like Khan Academy. So you've got, if you try to say it's 2.5 here, yeah, this thing would accelerate, but if this is 2.5 and 2.5, that thing wouldn't. So no go there. So in the end, we just left this as an unknown. We just called it FT. FT is unknown. And so for the 200 gram object M1, if you look at the, what do we call this, a lard? If you look at the lard for it, we know this force is 2 newtons. And we know it's accelerating upwards. So that means that the tension force has to be greater than 2 newtons. Okay, but I don't know what it is, so I'm just calling it FT. So if you look at the way this diagram goes together then, the unbalanced force here, well, algebraically, it's just going to be the difference between tension and 2 newtons. Okay, so the unbalanced force for object 1, tension minus 2. You pop over here to the other object and look at its diagram. It's accelerating downwards, so that means the unbalanced force has to be downwards. I'm just going to highlight the whole thing. So then, no, sorry. Thankfully, there's Control Z. That 2.5 Newton gravitation has got to be greater than the tension force. So that's why my unbalanced force for this object is written this way, 2.5 minus Ft. Okay? So where do you go from there? You come down to this thing, and this is the crux of the unit. Okay? That acceleration is the ratio of the unbalanced force to the mass. They have different masses. They have to have different unbalanced forces. So for object M1, we set up here that FU1 is Ft minus 2. So I just write Ft minus 2, and I write that over 0.2 kilograms. I can't wait till the next round of feedback. Mr. Harding, take it easier with the highlighter. It's hard on the eyes. Then for FU2 over here, it's 2.5 minus Ft. That's the FU, and I divide it by the mass. Different mass, different FU. Same acceleration, or at least it should be. Okay, it should be pretty darn close to that. So if we push through with this math, you get, oh gosh. So I've got 0.2 Ft minus 2. I've got 0.25 here. Okay, so what I did was I came from here. I came down here and I did some algebra. Okay? So I just multiply both sides by 0.25, multiply both sides by 0.2. So that's where this math happened. Did this happen in here yesterday? Okay, cool. So trust that some algebra happened, and you can go back and double check it later because I didn't go to West High. And in the end, this was right where we were getting at the end of the hour. Okay, so I multiply both sides by 0.25, multiply both sides by 0.2 to get this all on the top line. And then my only unknown is ft. So again, I just like what do people say, collected the terms or whatever. Okay, and eventually I get 0.45 ft equals 1. So ft equals 1 over 0.45. That shakes out to be 2.22 newtons. That meets our criteria. It's greater than the 2 newtons that this thing weighs, so that'll cause that to accelerate up. It's less than the 2.5 newtons that this thing weighs. That's going to allow it to accelerate down. Will it allow them to accelerate the same? Well, that's where I went back up in here and punched in some math. Let's get a different highlighter color. I bet that's a thing. Ooh. All right. So now I take this tension of 2.22 and I plug it in. Oh. And I plug it in for that. So I have 2.22 minus 2. Somebody check my math, but I think that shakes out to be 0.22 newtons. Okay. So I took this tension force and put it into my equation up here. So it's 2.22 minus 2. That's giving me the FU of 0.22. A lot of 2's going on here. And then I'm going to add some more to it. I'm going to divide by 0.2 kilograms because that's the mass. And I get an acceleration of 1.1 meters per second squared. If I do the same thing over on this side, I'm going to have 2.5 minus 2.22. Okay. That gives me the FU on object 2 of 0.28 newtons. They have different FUs. There has to be more FU on it. It's bigger. It's got to have the same acceleration. So it takes a bigger FU. So I take 0.28 newtons divided by 0.25 kilograms. Hey Siri, what is 0.28 divided by 0.25? That is the world's tiniest pass. 1.1-ish. Okay, more or less. Okay, so that's where we've got to land. We've got to land on the same acceleration for both objects because they're connected. Okay, because when it moves, that's what happens. You can't have one accelerating slower. They take different times to cover the same distance. That'd be weird. That'd be really weird. Okay, so we've gone in and used. It's not really a system of equations, but we've set up FU over m for both objects based on the understanding that their accelerations would have to be the same. Okay. Was this us? I feel like this is where we found out the time. Okay. This is a different approach at getting to the acceleration easierly. Okay. And what I've basically done is if you think about the system schema, I've got M1, I've got M2, I've got the Earth. I'm not considering the rope to be an object because ropes don't have souls. So gravitational interactions with the Earth, and then they're having a tension interaction with each other. But if I throw a system boundary around the masses, the tension is internal. Is it like a puzzle? If I put them all together, does it spell something out? All right. If I put a system boundary around M1, M2, that's why I'm ignoring the tension in this solution here. I'm just worrying about this gravitational interaction for M1, which is 2 newtons, and this gravitational interaction for M2, which is 2. Come on, buddy. 2.5 newtons. Okay. And then that's what's happening here. Okay. Inside the system is M1 and M2. That's a total mass of 0.45 kilograms. This is where it gets weird, kids. What I did was I said pulleys just change the direction of the force. So like effectively, like I unwrapped this thing from the pulley and you got heavy gravity that way, 2.5 newtons, and less gravity that way, just 2 newtons. So the difference between those two is the FU for the system. And I just moved my pen and here we go. And so that's how I got a system FU of 0.5. And if you take that system FU and divide it by the system mass, FU system over FU mass, that's going to be 0.5 newtons divided by 0.45 kilograms. That's going to be 1.1 meters per second squared. Okay? So these are the various ways that these cats get skinned. When you're doing problem solving in the unbalanced force particle model, at times it's more convenient to view it as a system. At other times, you're going to need to view them as individual objects. But the Rosetta Stone that gets everything back and forth is acceleration, which we've defined in here as.
Velocity over time.
Thank you, kids. Slope on a velocity versus time graph. We've also defined it as what now? Well, we have that, but we've also defined it as
over mass.
FU over mass, the ratio of unbalanced force to mass. We have two ways of knowing acceleration. That's crucial to solving everything in this unit. Okay, that's the unit there, kids. Now we just got to deal with different ways it gets deployed. Okay, Sarah, this thing. Have we started on this at all? Ish. All right. So what I'm looking for you to do is put your Bob and Jane solution together on a whiteboard. Okay. FBDs and HBDs in the boxes. Okay. And in the circle where we usually put the whatever, put your total time in there. Okay.
For all of them?
For the Bob and Jane. This is Bob and Jane.
Yeah,
so
like
part 1 of Bob and Jane,
4 parts.
part
Gotcha.
2, part 3, part 4, or do we need to do it like mathematically? Are mistakes mandatory?
Nah, never.
What did you say? I didn't hear what you
I
said.
don't like our conversations when they aren't, though. You're going to make some, so I kind of want them to be mandatory so it's not awkward later. How about this? How many people have seen the movie No Country for Old Men?
Mhm.
None of you?
I think it might
What's the
be.
significance of the coin toss?
That's not a coin.
Whatever. So we're going to play a game called No Mistakes for Old Men or something. No Country for Old Mistakes. So you're going to toss a quarter. If it's heads, then you got to make a mistake. If it's tails, no mistake.
No mistakes.
Too bad. I don't have any words.
It's just figurative. Come on.
This is heads.
Okay. So, we have to do 3 body diagrams for each of the individual pieces. Yes. Because,
Oh my god.
at least I'm going to start with that.
Whoa.
Bob and Jane.
Great.
Bob and Jane
Still
weigh
about pressure.
200, 900, 1500.
Yeah, I gotta go back and take my time.
Okay, here's number 3.
This is Bob and Jane. They together weigh 1,500. And this thing all together weighs 900.
Number 1. Bob and Jane are together.
900.
As soon as they grab hold of the roof, they slip off the roof, and the following unfortunately is unsafe while
Hey, so you're looking for bring recorders up today, sir?
Bob and Jane aim together, strike the ground.
I know, but like I'm wearing it today too, so I'm feeling part of the team.
F, E,
So what are we
F,
Oh, wait. Are we supposed to
Are
do
we
one
just
for
like,
Bob?
oh, that by diagram?
Oh wait, we don't know FFT.
No,
we
no.
don't know FFT yet, so we're gonna have to.
Oh, sorry, you don't call it a happy birthday.
Yeah.
Lard.
And then F,
Yeah, lard. Lines against radial. What do you call? What's a lard?
I don't know.
Large error return diagram.
Large error
Large
return
error.
diagram.
Large error.
Return
Large?
Return
diagram.
diagram.
Large.
Yeah.
Don't say
So
stupid.
weird.
Somebody here came up.
Wait,
Is that
Just
you?
free body diagram. Wow, that's a really good.
You're the one that remembered it. Okay.
You call it a first body diagram. That's up on the name.
We can solve that.
So,
Right? That's a pretty dumb name. That's the official.
so for most one.
I forgot what I was doing. Oh, so you can do find the acceleration by
Yeah.
F U.
Although there's a classic
Wait,
call.
what? Yeah, you can.
Two.
Because
They drop cats.
it's
Is there connecting arrows together?
Somebody in the test like,
mass
yeah,
voltage,
have a girl
which is
I should do that.
I know.
Yeah.
2,
So
4,
diagram, we didn't put
0, 0, 8. And 1/4 equals acceleration. Ta-da! So then we use that.
Ideal model.
This one is.
1/4 meters.
Yeah, but.
Oh, I didn't show you the video.
0.
So, you know, like,
10 meters.
Oh wait.
So,
Are we doing just the
10
first one now?
fourths is final velocity.
yeah, that one.
No, that is it.
Oh, I get it now.
Hopefully I'm doing this right. I know.
You guys are the book flicks generation, right? You guys watch book flicks?
Oh, yeah, he's in
Where like you don't read the book, you just watch it video.
So how do you work this?
You don't know how to like read something.
All right,
Go with.
All
All right.
You guys are going down. Yeah, he needs to come down.
All right, here's what this worksheet is based on. I should probably show you this.
Oh, we did.
If
I
you do it
like how let's draw it out. Yeah, we'll just draw it like this. Like this.
No free ads.
Then you're not
This one's a barrel of bricks. Oh, so the guy is trying to take bricks off of a roof and the barrel's too heavy and it drags him up, hits him on the way up.
Cracks his skull, injures his collarbone, keeps shooting straight up until he's about 2 knuckles deep into the point.
Of course, the barrel exploded when it hit the ground, losing the load. And his weight was obviously heavier than the barrel's weight.
The barrel goes back up, and this guy goes back down. He hits the barrel about halfway down.
I've even heard that he then let go of the rope and what was remaining of the barrel came down and hit him. But he survived. Yeah. So we're going to replicate that. Yeah, it's going to be tricky. This is a study in physics and bad luck. Victim holds rope. Heavy barrel pulls him up. The barrel breaks and loses his load. Victim falls. Victim lets go of the rope. Gravity does the rest.
But we don't need attention for the first one.